Section 3.4, Derivatives as Rates of Change. We've talked about this all semester, that the slope of the tangent line is used to approximate the rate of change for a nonlinear function. Then we learned that the slope of a tangent line is the same thing as the derivative of a function. So in this section, we're bringing all of those ideas together. If we want to talk about how much a function is changing, we could use one of many formulas, one of them being an amount of change formula. On the screen, you see a blue function. That's the function f. You also see a red line, which looks tangent to the blue function at the value x equals a. That's the orange dot. If we want to calculate how the blue curve is changing, we could move forward from the orange point some distance h. The new x value would be a plus h. We could plug that into our function to find a point further up along the blue curve. That point would be located at a plus h, that's the x value, and f of a plus h, that's the y value. So to answer the question, how is f changing? All we would need to do is find the difference in the y values. So I have this y value, f of a plus h, and I have this y value, f of a. So to find out how f is changing, I just find the difference between those y values. If I wanted to rewrite that as the average rate of change, all I would need to do is take the amount of change and divide it by the interval. Now in this case, the interval, that's the horizontal distance between our 2 points. We traveled a distance of h to find that second point, so our average rate of change is just the amount of change, the change in y values, divided by h, which is really the change in x values. We could also talk about the instantaneous rate of change, which is the derivative, which we know is the average rate of change with a limit where h gets to get smaller and smaller until eventually it is infinitely small or zero. And what we want to talk about in this section is how the average rate of change and the instantaneous rate of change are almost identical when we let h become very, very small. Now in this case, we might not see that. If we were to draw a secant line between this top point and the orange point down here, that line would look very different than the tangent line that we have. But that's because here I'm using a pretty generous size for h. Notice that we've spanned about 2 units, so that's pretty big. If I had made h much smaller, maybe I stopped it right here, then I would look at the slope between these 2 points instead, and I would compare that to the slope of the red line. The average rate of change and the instantaneous rate of change here look very, very similar because h is very small. So for small enough values of h, we can say that the average rate of change and the instantaneous rate of change are about equal, which is what I have stated here on the bottom left of the screen. And if we say that these are about equal, then we could solve this expression for f at a plus h. So all we would need to do is multiply by h on both sides. That would get rid of the h over here. Then we can add f of a to both sides. That would get rid of the f of a here. And then we're left with f at a plus h is about equal to f at a plus h times f prime at a. In the picture, what I'm saying is that if we pick h to be small enough, which I've already admitted in this diagram h is too big, but if we were to pick h small enough, then the point that is here on our tangent line and the point that is actually on our function would look so similar that we couldn't tell them apart. And so we can use this idea to make estimations about our function at future points with only knowing two things. We need to know the value of the function at a, and we need to know the value of the derivative for that function at a. This can be useful in applications like population. We know what the current population is today, and we can do a pretty good job of expressing how that population is growing at this current moment. And we can use that to predict the population for maybe next year or the year after that. We wouldn't want to use that to predict the population 3 centuries from now. That would be too large of an interval difference. But 1 or 2 years, that would be a small enough h for our prediction using this approximation to be good enough. To really drive home the idea that we only need these 2 facts to make a prediction about future points on our function, we're going to do a couple of examples where we don't even know what the function definition is. We don't know if it's a quadratic, we don't know if it's an exponential, we have no idea. The only things we know are the function value and the derivative value at the same point. And we're going to use that to estimate the function at a future point. So using that approximation, we will say f at 3.2 is equal to f at 3 plus some h value times f prime at 3. Now to find the h value, we need to look at the x value we're making our approximation at, and the x value that we know function information at. So we need to look at the change in those two things. We see that h has to be 0.2 because that's how different these x values are. So we can replace h with 0.2. We know that f at 3 is 2, so we can replace f at 3 with 2. And we know f prime at 3 is 5, so we can replace f prime at 3 with 5. And then we multiply through, we have 2 plus 0.2 times 5 is 1.0 for a final answer of 3. So we don't know what the function definition is. We did not plug 3.2 into the function to find out the function value. Instead, we used this approximation to figure out what the function would look like according to the rate of change that's happening at x equals 3. Let's try another one. Here we want to estimate the function value at 10.1, and we're going to use information of our function at x equals 10. So we can see h would have to be 0.1. Then when we make our approximation for f at 10.1, we can use f at 10, which is -5, plus h, 0.1, times f prime at 10, which is 6. So we have -5 plus 0.6, which comes out to be -4.94.